Okay, good afternoon, everyone. It's my pleasure today to introduce our latest technology for automated nucleic acid extraction called SmartExtraction from Analytik Jena. I'm waiting for slide changing. Okay, before talking about the details of the technologies, I would like to briefly introduce myself. My name is Sinothai. I'm a product specialist from Analytik Jena Far East, based in Bangkok, which is a subsidiary of Analytik Jena AG, having headquarters in Jena city of Germany. And I'm responsible for providing technical and application support to the users in Southeast Asia, plus Australia and New Zealand. Also, I'm involved in the installation of the new systems, as well as providing training to the users. Today, I would like to talk about these topics. First, I want to walk you through a brief history of nucleic acid extraction, and then I want to introduce you the SmartExtraction, which is our latest extraction technology. Then I want to give you some examples of using SmartExtraction for automated nucleic acid extraction. And then I want to compare SmartExtraction with other extraction technologies. Later, I want to highlight a special feature of SmartExtraction, which is extraction of high molecular weight genomic DNA. Finally, I would like to wrap everything up and provide you a summary. Okay, let's begin with the history of nucleic acid extraction. First isolation of nucleic acid came in 1869, from a Swiss physician named Friedrich Miescher. He isolated DNA whose chemical composition or structure were not known at the time from white blood cells, and he named the molecule he isolated nuclein, which was later termed nucleic acids as we know today. His extraction method involved a lot of washing steps with sodium sulfate and alcohol, filtration and settlement of cells, as well as alkaline extraction and acidification. The extraction procedures was quite lengthy and complicated. Also, use of toxic chemicals. Since then, the DNA and RNA have been actively studied, prompting the demand for more practical method for nucleic acid extraction. Almost 100 years later, the Phenol-Chlorophorm extraction was invented, and this technology relies on the use of mixture of phenol-chlorophorm to cause phase separation, allowing nucleic acid isolation from other organic substance. Although if done properly by experienced user, the technique can yield quite good quality of nucleic acid. The use of hazardous chemicals like phenol-chlorophorm, also risk of contamination, as well as time consumption, led to the development of easier methods for nucleic acid extraction. The silica-based nucleic acid extraction came later, and it is a basic principle of most commercially available kits in the market. This technology relies on the use of cheotropic salt buffer with high amide strength to promote nucleic acid binding to silica matrices, which can be in the form of a spin filter, suitable for manual extraction, or in the form of silica-coated magnetic beads, suitable for automated nucleic acid extraction. The technology provides ease of handling. However, there is a risk associated with salt contamination due to the use of high salt cheotropic buffer to promote DNA binding. Later, we thought that we want to circumvent this disadvantage, so we developed advanced silica-based nucleic acid extraction. We call it dual chemistry technology. This technology, instead of using high salt cheotropic buffer to promote nucleic acid binding to the silica, we use the combination of cheotropic and non-cheotropic salt buffer with a low ionic strength to promote nucleic acid binding to silica matrices, thus reducing the risk of salt contamination. Also, lysis procedures become more efficient because the proteolytic enzymes used, such as proteinase K, can work more efficiently in less cheotropic conditions provided by the technology. And handling is still as easy as the conventional silica-based extraction method. Later, we thought that we could further improve the dual chemistry technology. And recently, we launched Smart Extraction as an improvement of our dual chemistry technology. With this technology, there is no need of ionic change procedures, no spin filter columns, no silica suspension, no silica coat magnetic beads. It relies on binding of nucleic acid to the smart modified surface, making the extraction procedures easier, suitable for automation. Currently, we have extraction kits based on this technology for both manual and automated extraction. For automated extraction, we have extraction kits based on this technology for general starting material like tissue, bacteria, yeast. Also, we have specialized kit for blood samples and plants. For manual extraction kits, we have kits for general starting material as well as a kit for blood samples. How does the smart extraction work? For manual extraction, the whole extraction process takes place in a tube containing smart modified material. After lysis, the lyse sample is transferred to the tube containing smart modified material, shown here as a black pellet, and it's exactly pellets like this. Yeah. And the binding of DNA in the lyse sample to the smart modified material is promoted by the action of shaking using thermoshaker. After the binding, magnetic rack is used to collect the smart modified material, and then the DNA bound to smart modified materials are washed with a washing buffer, and clean DNA bound to smart modified surface can be released from the material using elution buffer. So the whole extraction process for the smart extraction manual doesn't need centrifugation. Only thermoshaker and magnetic racks are needed. How automated smart extraction works? Instead of using smart modified material in the tube, we put the smart modified material in the pipetting tips of the robot, the liquid handling robot. Yeah. And then the robot will complete the extraction task. In brief, during binding, the robot will bring tip containing smart modified material to the lyse sample and then perform pipetting up and down to allow DNA present to bind to the smart modified surface. During washing, the robot will bring tips containing DNA bound smart modified surface to the elution buffer cavity, and then perform pipetting up and down for washing. After the washing has completed, the robot will just blow air to dry the smart modified material. And for elution, robot brings tips containing smart modified material with DNA bound to the illusion buffer cavity, and then pipetting up and down, so the DNA will be released to the solution. So automated smart extraction complete all necessary extraction steps, including lysis, DNA binding, washing, drying, and elution. But from robot side, only pipetting up and down in different reagent is needed. Therefore, the procedures of extraction is simpler compared to that of magnetic bead-based extraction technology. And smart extraction has been optimized for use in conjunction with our liquid handling systems for automated nucleic acid extraction. These are robots of different throughput levels for different application needs. But it also has a potential for use with other liquid handling platform, because what is needed for extraction is smart modified material in the pipetting tips. I would like to show you some examples of extraction using smart extraction on our low to medium throughput nucleic acid extraction system called InnoPLC16 Touch. This is a device, a standalone device controlled via internal tablet here. This device, in conjunction with smart extraction, can extract DNA from 1 up to 16 samples in parallel, and the kits come pre-filled in the sealed plastic, reagent plastic, minimizing the manual preparation before automated extraction. This slide shows a result obtained from using smart extraction on InnoPLC16 Touch to extract genomic DNA from 16 samples of 2 mil PBMC. The extraction workflow consists of 20 to 30 minutes of external lysis of erythrocyte, and followed by automated extraction of about 38 minutes. And we got a big bulk of genomic DNA as determined on Abbott scale here, confirming the good yield and good quality of DNA obtained. Also, we test smart extraction on InnoPLC16 Touch with minced meat, as shown here, our result. The extraction workflow took 30 minutes for external lysis, and automated extraction takes 20 minutes, and we got good quality and good yield of DNA as determined on the Abbott scale analysis. Also, the smart extraction can be used with difficult starting material like mouse tail, as shown here. Follow 90 minutes of external lysis, automated extraction to 20 minutes, and we got good yield and good quality of DNA from the extraction. Also, for higher throughput requirement, we have FelX, which is a liquid handling robot, which when used in conjunction with smart extraction, can perform nucleic acid extraction from up to 96 samples in parallel. With our tip sealing technology, we don't have a risk of spillover, carryover, or no contamination. And the elution volume can be adjusted as desired within the range of 150 to 500 microliter. And now we are targeting high throughput nucleic acid extraction from whole blood, PBMC, tissue sample, rodent tail pieces, eukaryotic cells, bacteria, and yeast. This slide shows result from using smart extraction in conjunction with the FelX extraction systems to extract DNA from 96 samples of 500 microliter whole blood samples. The extraction took 100 minutes, and we got good quality and good yield of DNA. This also, I want to mention that for the workflow, these include the internal lysis, meaning that we load the whole blood. For this protocol, we don't need the external lysis. This slide, I want to show you some comparisons of smart extraction with magnetic bead-based extraction. The upper left graph compare the yield of the two technologies using different volume of whole blood from 1, 2, and 3 mil in duplicates. Yeah. The yield from mag beads are shown in red columns, and from smart extraction in black column. We can see that using 1 mil whole blood as starting material, we have quite comparable yield of DNA between two technologies. However, at 2 and 3 mil of whole blood as starting material, smart extraction gives increasing yield proportional to increasing volume of starting material, suggesting that the material has a higher binding capacity. Also, the ratio of 260 and 280s of two technologies are comparable, suggesting comparable purity obtained from these two technologies. However, smart extraction tend to give a higher ratio of 260 to 230 compared to the magnetic bead base for blood sample. Also, we compare smart extraction on our extraction system with the manual spin filter based extraction to extract equal amount of rodent tail samples. After enzymatic lysis for 2 hours, we perform extraction with smart extraction as well as manual extraction. Both methods took roughly the same time, 15 minutes, but smart extraction gave higher yield, more than double that of spin filter-based technology. Also, we compare smart extraction and spin filter-based technology on extraction of yeast DNA from yeast samples. And we found that the smart extraction gives a higher yield as well, as shown here on agarose gel. Also, we analyzed the DNA fragments obtained from smart extraction. We use PFG, pulse field gel electrophoresis, which is a technique used for separation of large molecular weight DNA to analyze the result from extraction of DNA from E. coli strains using smart extraction. We found that DNA extract were in the range of 30 kb to up to 500 kb. And when compared to DNA fragments obtained from spin filter technology, we got much lower DNA fragment, and we don't find DNA larger than 47 kilobase. Also, smart extraction gave higher yield compared to spin filter, as we have already mentioned. Also, we observe high molecular weight genomic DNA from using smart extraction with blood samples. Yeah, with the PFG gel, we found the DNA fragment extract in the range size of 50 to 400 kilobase. These are sizes suitable for application like long-read sequencing, like nanopore sequencing. So this has come to an end of my talk, and I would like to provide you a summary. Smart extraction is the latest extraction technology from Analytik Jena, which has simple extraction procedures suitable for both manual and automated extraction. Being simple, extraction process is faster compared to that of magnetic bead-based extraction. because there is no need of a step of magnetic beads collection, which normally take a little bit of time. Also, because of the higher binding capacity of the material, we tend to get a higher yield of DNA when use the same amount of starting material. And the technology is liquid handling platform independent. And so there is possibility to use smart extraction on other platforms. Also, smart extraction yields high molecular weight DNA from the extraction. I would like to thank you for your attention, and I hope to address some of your questions if you may have. Thank you. No question? Okay, I would like to mention that we have a local partner in Indonesia. If you are interested in our product or want to know more details about our technology, please contact PT DIASTIKA BIOTEKINDO as the contact shown here. Okay, I got it. Okay, I would like to address the first question is, can we reuse smart material? How long for shelf life? Theoretically, smart extraction can be reused, but concern over cross-contamination, I would recommend not to do so. Yeah, please use the new smart modified material for the new extraction because your samples are more precious. Shelf life, about two years, 24 months, sorry. Okay, the second question is whether we have experience with using smart extraction with COVID-19. Okay, that's a good question. At the moment, we are developing smart extraction for RNA, so it's in the pipeline. So it's not ready yet, so we haven't tested with the RNA virus in this case. But we have solution for COVID-19 or for extraction of virus RNA for COVID-19 testing. So automated extraction. Okay, second question is how long using automated extraction for COVID-19? It's about 90 minutes for the extraction of 96 samples in parallel, up to 96 samples in parallel. Okay, thanks for your question. And I hope that you enjoy this seminar. Okay, I would like to end this session now. Thank you. Sorry.